on in vivo myelo-architecture using whole brain diffusion MRI.
Thanks. So this is now quite a change in tack to the previous talks for two reasons. One, there's not going to be any epilepsy in this talk. It's about an imaging method. Hopefully we'll have a role in epilepsy. And the second, because it's a much shorter talk, I thought we only had 10 minutes, so that may be good for you. I don't know, we'll see. So I'm going to be talking about a new approach we have to measure myeloarchitecture in the brain, in the human brain. One of the ideas of cortical myeloarchitecture is to parcellate the cortex in regions based on the spatial organization of myelinated fibers. And this has received huge interest in recent years in MRI, and have been many methods using more conventional approaches like T1, T2, and T2 star weighted imaging, typical parameters from MRI. And they tend to be used as a surrogate marker or marker of myelin. So for example, we have on the left using T1 weighted or T1 mapping, T2 star, and the group that has had the major impact, that is from David Van Essen, they use a combination of these T1 and T2 weighted images. And in general, we can see in all of them, if you focus on this one, high signal with this surrogate measure, myelin in visual areas, auditory areas, sensorimotor among others, and low in the frontal and temporal and other areas too. And all these techniques, they have advantages and disadvantages. None of them is obviously perfect. So from the diffusion MRI, that is the approach that we are using, in recent years have been huge improvements in hardware, acquisition methods, and analysis methods, and these have opened up the possibility of really starting looking at cortical myeloarchitecture. And most of the studies so far have been done on ex vivo samples, looking at really detail of the cortical structures. For example, this is a group from Holland, and they took a specimen of the human visual area, where's the mouse? B1 and B2, and they can start seeing the layers and the stria of Gennari, and that is different in the B2, it is mainly radial and things like that. So they can do very detailed analysis, and some preliminary analysis that is promising. This is from NIH. They were studying at a region around the sensorimotor area using diffusion tensor metrics, so not very robust metrics, let's say. And then they were starting to see some of the patterns that they were seeing with these other methods. So the aim of this study was to investigate if we could use more advanced diffusion MRI and better quality data that is currently now available to see whole brain and in vivo brain myeloarchitecture. So regarding the data, this is not a standard data. It's data from the Human Connector project. This is a big project from NIH funded that in particular, they have in simple terms, would be they have a normal clinical standard like the ones in Melbourne, but they improve it and they have huge powerful hardware. So if you take, I don't know, a car, a Toyota Corolla, and then you stack a V8 engine, it's that kind of thing. You can't compare it with a standard clinical scanner, but the shell that they are using is the same one. And in particular, it lets you acquire, for those interested in diffusion, images that are faster, better signal-to-noise ratio, and much finer detail. The pixels are much smaller. But this type of scanners, you won't see them appearing in the next few years in the hospital because, for example, to run this scanner, they need the same power that you need to run a power submarine. So really, it's a ridiculous amount of power they need to run these things. And then we also use the data they have for anatomical imaging for the processing, and we did the standard pre-processing that they recommend for the pipeline for the human connection study. From an analysis point of view, we also use something slightly different to the standard approach. It's a method that was developed in our group recently, and it's an extension of a method. Again, those of you familiar with diffusion imaging, you may have heard it's a method we developed now quite a few years ago in 2007, known as constrained spherical deconvolution, that it lets you calculate the fiber orientation distribution. So if you look at a zoom of an area in the brain, it lets you calculate these blobs where it tells you in each box in the brain what fiber populations and how much of each of them you have. And it has been very, very powerful and very useful, used all around the world for white matter. So in the white matter structures, it's very good, but when you go to structures like CSF, obviously there shouldn't be any fibers there, or this is wrong, gray matter, or even the interface, you get lots of artificial peaks that they are not real. And it's just, so the technique is usually limited to white matter is where things are working well. And this is what this other method extension that was developed recently by a group is known as multi-tissue constrained spherical deconvolution, is to extend and correct for these problems. And in particular, needs slightly more amount of data. This multiple p-value data, this means acquire data with different amount of diffusion weighting, so it's not your standard clinical protocol. And I'm not going to go into detail into the methods, but it's a multi-compartmental model where you can model white matter, gray matter, and CSF. And in particular, what you can do is remove the partial volume information contamination that was from the isotropic component. Where is the mouse? Hello, mouse, come back. So you can remove all these things that we're saying that come from gray matter and CSF, the isotropic bit that you don't want. And in particular, you can calculate for this study, the other things you can calculate, but for this study, what we're interested in is the fiber orientation distribution. So these blobs, but now in the gray matter. So what we're looking at the orientation dependence part of the signal, the diffusion signal in gray matter. So if I lost you in any of these, the only thing you have to remember from this is what we are able now to calculate with this method is these blobs, but in the gray matter, in a robust way. Then for quantitation, what we do is we calculate the total of these fiber orientations, so we add all the information along all the possible orientations. And for those of you that were here last session yesterday afternoon, this is equivalent to having all the orientations of the apparent fiber density that's shown at talking in her presentation. And then for display, we use what is standard in this myelo-architecture field that is using free surfer to display things in an inflated brain. So what kind of results we get? So this is looking now at a little region in the sensorimotor area in the central circles. And this is what you would get with your standard constrained spherical deconvolution. This is a method commonly used. And you see you get very good, nice results in the white matter, but the gray matter and the CSF is all a mess. And then if you look at what you get with this multi-tissue, it cleans, if I zoom swap between the two, you can see that it cleans up all these regions, and you start getting now, you can start seeing, radial, for example, in this area, radial projections in the cortex, and start to get information that is sensible. But at the same time, when you look at this picture, it looks odd because you get high signal, a high amount of information here, and suddenly it drops and disappears. So around this area, it seems to all go away. Is this an artifact? Is it real? Well, it turned out that it is real. So if you look at myelin staining in this same region, that is the transition between the area 4 and area 3A, which have very different myelin content and therefore and very different organization. And this is what the kind of things that we can start picking up with these methods. And out of interest, again, if you take this data here and now you scale it, just so all of them have the same area under the peak, just to see, I'm going the wrong way, what do you see? There. So these two are exactly the same, but simply scaled up, so they all have the same area. The interesting bit is all these areas that they have very, very little. You see it here. You couldn't see much at all. There is actually very coherent information, but what it's telling us is that the component, the amount compared to the whatever there from the diffusion, from the gray matter, it was only a tiny proportion of that one is really a coherent structure. The rest is all pointing in all funny directions. But the remaining one that is there, it is and is coherent. So then for what we did is we take our 8 subjects. This was we take 8 subjects from the large data set they have there. And I'm showing now here population average results. So these are now this total fiber orientation distribution seen from the top in the pile surface. And you start to see that these clusters in intensity in regions. So we can see a sensorimotor area, the visual area, low in the front. Maybe it's easier to see if we open up and you see from the sides, or if it's more common in this field, if you inflate it so you can start seeing inside the jar. And then you get this kind of structures. It's roughly bilateral. You can see it's not exactly one-to-one, but the structure seems to be in both sides. And if we look in more detail, you can see that you get high signal, or would be in our surrogate marker, high myelin, in areas around the sensorimotor area. The interparietal circles, another one that has been characterized by other methods to have very high myelin. Supplementary motor area, frontal eye fields, auditory areas, visual areas, B1, B2, another MT+, the medial temporal complex, another visual pathway-related area. So all these areas have been characterized by other ones before, so they are known to have high myelin, and also areas that are known to have very low myelin, like the anterior temporal and the frontal lobes, that are also like that. So just for comparison, this is much larger study that they did with almost 70 subjects and on a different method by the group of Van Nessen. You can see that in general, the patterns that we are seeing are similar to the ones that they are seeing with other techniques. So this gives some confidence that what we are starting to see, it is real. It's not an artifact of the method, but it's actually telling us about a gray matter property. And just for those of you interested in more on the technical side, this is the image I was just showing before. This is with the newer method. If you were to do exactly the same in the same 8 subjects, but with the old method, these are the patterns that you get. So it's nothing to do with what you expect. You see, for example, you see high signal now in the front. The sensorimotor is wrong. So you need to have this advanced analysis to really see these patterns of myeloarchitecture. So just to finish off, hopefully you can see that now diffusion MRI provides a new tool, and it's a quantitative tool to study cortical myeloarchitecture. So if you want to see one more tool that can be used from MRI non-invasively to look at these properties. And it's important that it can be done in vivo and whole brain. And the patterns that we see with these parameters, the total fiber orientation density, is similar to the ones seen both in other MRI methods or other histological methods. And therefore complements both those methods and also the methods that have been done in diffusion to look more at the, with ex vivo at the cortical, intracortical layers and things like that. The contrast that we obtain with this total fiber orientation density, if you want, it relates a bit to what it looks a bit more, what we call the white matter-like fibers in the cortex. So those fibers that they are coherently oriented within the cortex. So therefore, when we see high signal in this parameter, what we are looking is an increased microstructure organization within those cortical regions. This also provides some evidence that the diffusion MRI not only can now be used for white matter that has been used for a lot, but also with these more advanced techniques can be started to use also for looking at gray matter. And this is where maybe there could be the link with epilepsy. And the current analysis which I'll show here is with the data, this fancy data from the Human Connector project, but obviously what we're doing now is looking at data that we can acquire in our scanners, seeing what type of protocols we need to be able to start to see these effects in more standard scanners, if you want. And that's it. Thank you for your attention. Great.
And how good is this going to be in terms of its noise characteristics? Can we see an N of 1 and characterize an individual subject?
Yes.
As a brain development?
Yeah, so for the Human Connector project, you could see it, and that's how, if I step back of how we started doing this project is when I look at the data that was published of this fancy analysis, the multi-tissue CSD, I could see these patterns that are, just by looking at things, are they real or artifacts. So I just try one data set to see if they're real or artifact, and all these patterns appear. So for the Human Connector project, N = 1, you can see this pattern. Obviously, it's much noisier as you expect. You will need to do some smoothing and things like that. What is more doubtful is in your, the scanners that we have, or the scanners here at the hospital across the road, are you going to be able to see with N = 1? That may need a lot of optimization of protocol and maybe a bit longer acquisitions. At the moment, this is what we are trying to determine. Any questions? Because obviously, if we're able to do N = 1, the interesting thing of this would be, start looking even cortical malformations, cortical dysplasias, and things like that, and see what but even if we are not able to do the full myeloarchitecture, it might give us an idea that the things that we're starting to see with this multi-tissue CSD into those gray matter structures, we can trust it, and we can start tracking inside the cortex and see what are the connections in the cortex and what are the patterns. So although we may not be able to do a whole brain myeloarchitecture, it may tell us that, well, we can trust looking at a focal area in a lot of detail. But something we have to do and try.
So with the previous CS or
CSD, let's call it standard, yeah.
I guess a lot of people have done tractography.
Yep.
And so how will this new method affect tractography?
Yes.
I guess it's affecting, where the grey matter meets the white matter. I don't know how.
Yeah, so if you're in the bulk of the fibers, then there is not much difference between the lobes of the CSD and the multi-tissue CSD. But in the one, I don't know if I should come back. Oh, it's too late now to go back to the. But even as soon as it doesn't need to be approaching the gray. As you know, the voxels that we use are very big. So even in the white matter, you have a lot of partial volume. They say as soon as you get closer to other areas in the grey matter or the CSF. So those ones, even in those areas, the white matter will be very different. But the key strength of that would be more approaching to the areas partial William with grey matter or CSF here. For your standard tracking, probably it's enough the CSD and then you have. But we tend to stop in close to the white matter, the grey matter interface.
Right.
Okay.